So here we've got the upper arm and the forearm. The upper arm or the forearm is attached to a bracelet, which is attached to a spring scale. So we can measure how much it's pulling, how much force it's pulling with. Because the point of a spring scale is to just measure amount of force. So you've got your bicep, you're flexing, you're pulling on this bracelet with a force of 180 newtons. And we want to know, among other things, how much force does the muscle have to pull with? The bicep muscle itself is attached over here near the elbow joint. We want to know how much force it's pulling with. And to figure that out, what's the one object we should probably be analyzing here? What's one object where all the forces we care about are acting on?
Either the bicep or the spring, maybe, or the pivot point.
Well, those are all going to be influencing the object we care about. But if we take a look at all the forces, the muscle's pulling on something, the spring's pulling on something, the joint is attached to something. What's the one object that all those forces are acting on?
Like the elbow?
I would say the elbow is really more providing one of the forces, because notice that the muscle isn't attached to the elbow. The spring isn't attached to the elbow, but they are all attached to, sorry, what was that?
The forearm, maybe?
Yeah, I think the forearm itself would be a good object to consider here, because we've got a spring force pulling the forearm to the right. We've got the muscle force pulling the forearm to the left. The elbow itself is holding the forearm in place with its own force from the joint. So the forearm has lots of forces acting on it. We know something about some of those forces. We at least know the strength of the force from the bracelet. And we're trying to figure out one of the other forces acting on it, the muscle force. So the forearm would be a good choice for an object to analyze here because there are so many forces acting on it that we either know or want to find information about. So let's treat the forearm as an object. If we draw out a free body diagram for this, we just treat the forearm as a single point. We can draw out all the forces acting on the forearm as arrows. And specifically, what forces should we include here? What forces are acting on the forearm itself?
Gravity, spring, muscle, or bicep. And then I don't really know what would be the opposite of gravity, like a normal force.
Well, let's fill in those first and see what else we can decide on. We've got gravity force pulling down. And how strong is that?
30.
Yeah, it tells us the weight of the forearm is 30 newtons and weight is the force of gravity. So 30 newtons. And yeah, we'd also have the spring force, as you mentioned. The spring force is just pulling, presumably the spring is stretched, so it's going to be pulling back towards the right. So we've got a spring force of 180 newtons. And the muscle is pulling in which direction?
The opposite of the spring.
Yeah, because the muscle, you can think of the muscle as a rope with tension in it. It can pull, but that's all it can do. So the muscle is going to pull more or less directly to the left. Perhaps it might be more realistic to say to the left and a little bit down, but I think just to the left would be a good approximation here. So that's force of the muscle, force of the bicep. And we don't yet know how strong that is because it may be partially counteracting the force of the spring. But what other forces involved here? What else is the forearm attached to?
Like the pivot point?
Yeah, the pivot point itself, the joint in the elbow. That could be exerting a force in essentially any direction to hold the forearm in place. The idea is these forces aren't making the forearm accelerate. We know, for instance, the forearm isn't just falling straight down. So the elbow joint at least has to be providing an upward force. It might also be providing a side-to-side component. Maybe the force of the elbow is somewhere diagonal, because we don't know yet if the force of the muscle and the force of the spring happen to cancel each other out. So we don't really know the direction of the force of the joint. And we also don't know how strong it is. For the muscle, we know the direction, we just don't know how strong it is. For the elbow joint, we know it's going to have an upwards component, but we don't know whether it's up and to the left or up and to the right or straight up. So we're going to need to run a little more analysis to figure out which one of those it actually is. Any questions on that so far?
What is the subscript on the vertical force?
This one,
Yeah.
force of the joint, so F joint.
Oh, okay.
That is force provided by the elbow itself, because the forearm is attached to the elbow joint, and a joint or a hinge or an axle like that can provide as much force as is needed to hold the object in place. Like for instance, if you've got a wheel with an axle in it and you tap on the edge of the wheel to make it start spinning, you're applying a force, but the wheel doesn't like start to fall or accelerate or anything because the axle is providing an equal and opposite force to hold it in place.
Okay.
So the joint or the hinge or the pivot point or whatever you want to call it is typically going to provide as much extra force as is needed in whatever direction is needed to prevent the object from sliding away. So in that case, what do we know about all of these forces acting together?
They add up to 0.
Yeah, the forearm is not accelerating, so we know that the forces acting on it have to add up to 0. We can say for certain that the sum of the forces on the forearm add up to 0 because the forearm is not accelerating. In fact, in this case, it's not even moving. But if it was moving, what we care about is it accelerating or not? And since this is a two-dimensional problem, this equation with force vectors, any equation with two-dimensional vectors is effectively two equations. We can split this up into the sum of the x components of the forces add up to 0, and separately, the sum of the y components of the forces add up to 0. So if we look at just the x components, how many of these forces, or which forces even have x components?
Possibly the top 3, but at least spring and muscle.
Yeah, we should definitely include the spring force and the gravity force. And the joint force may have an x component, so we should include it as, at least as a possibility. Force of the joint, I'll just write that as fjx. Gravity, however, is straight down, so it has no x component at all, so we can leave that out. So I should write that as force of the muscle, not force of gravity. Also, one other useful shortcut we can use, if we write out force of the spring, what is the x component of force of the spring?
The magnitude, 180.
Since it's purely in the x direction, its x component is the magnitude, and its y component would be 0. So we can say the force of the spring is 180 newtons, comma 0. Its x component is 180. So we can replace that with 180. And also for the muscle, we don't know its magnitude, but we at least know it's purely to the left. So we can write that as its x component would just be negative its magnitude, since it's in the negative x direction, and its y component would be 0. So the force of the muscle in xy component form, we can say its x component is negative its magnitude, and its y component is 0, which means adding the x component of the force of the muscle is equivalent to adding negative magnitude of the force of the muscle. So we've got 180 newtons plus negative force of the muscle plus the x component of force of the joint, whatever that happens to be. And what about for the y components? What do we know about the y components here?
Gravity and possibly joint.
Yeah, force of gravity in the y direction, force of the joint in the y direction adds up to 0. And it looks like we're definitely going to have a force of joint y component, because there's got to be something to cancel out the force of gravity y component. Also, what is the force of gravity y component?
180.
That was the spring, I think. The force of gravity is very strong.
30.
Yeah. And since that's purely in the y direction, straight down, we can write that as 0, negative 30. So the y component of gravity is negative 30 newtons. The y component of the joint is unknown. At this point, we have two equations, one equation for the x components, one equation for the y components, excuse me. But how many unknowns do we have?
We only have one in the y equation.
Overall, I mean that.
3.
Right, we've got 3 unknowns, but only 2 equations. Mathematically, that suggests we're going to need one more equation to get a system of equations we can solve. And we can use the shortcut of solving this second equation immediately, because as you said, this equation has only one unknown. So you can solve that right away and get force of the joint y component has to equal what?
30 newtons.
Positive 30 newtons. So we've reduced this to only 2 unknowns. We don't know the x component of the force of the joint, and we don't know the strength of the force of the muscle. And we only have one equation remaining now that we've used up this equation to find one of the unknowns. So we still need one more equation. If we effectively just have one equation with 2 unknowns, we're going to need one more piece of information, one more equation. We can get that though, because if this forearm is just staying rigidly still, what else do we know other than forces? What else has to add up to 0?
Torque.
Yeah, we can also say the torques have to add up to 0. Because torque is the rotational version of force. If there's no translational acceleration, you know the forces add up to 0. If there's no rotational acceleration, you know the torques add up to 0. Rotational in the acceleration in the sense of changing how fast it's rotating. Or alternatively changing the axis. Like let's say you've got something spinning like this, and it rotates to be spinning like this. If you change the axis it's rotating around, that counts as rotational acceleration, because rotation has direction associated with it. For example, let's say you have an object that is moving and then changes the direction of motion. That counts as acceleration, even if it doesn't change how fast it's moving. Likewise, if you've got an object that's spinning and you change the axis it's rotating around, that counts as rotational acceleration, even if it's not changing how fast it's spinning. So rotational acceleration means either you're changing how fast the object is spinning, or you're tilting the axis it's rotating around, or maybe both. And either one of those requires a torque. In this case, though, the forearm starts off not rotating and continues to be not rotating. So we know the torques have to add up to 0 because there's no change in the rotation. So we can say that as well. The sum of the torques, usually written as the Greek letter tau, adds up to 0. In general, anytime you know that an object is not rotationally accelerating, then you can assume that the torques add up to 0. No change in the rotational momentum. And for torque, torque is related to force, but torque involves other information beyond that. Torque is all about force and what else?
Distance.
Yeah, force and distance, specifically distance of the force from where?
Pivot point.
Yeah, distance from the pivot point. In this context, what would we treat as the pivot point?
The joint or elbow.
Right. The elbow joint itself is the pivot point. So we're going to be measuring all of the locations as distances from the pivot point. And what are the locations we care about?
The center of mass.
Mm-hmm.
And the distance of the bicep and the spring.
Yeah, all those distances are going to be the R values we use in the torque formula. Torque, and that means we're going to have to care about where those forces are. The usual way we would calculate torque first of all, torque is a vector. It does have direction associated with it. But if you're just looking at the magnitude, how do you usually calculate magnitude of a torque vector? Do you have any formulas for that yet?
Like the R perpendicular times force?
Yeah, one way to do it is to multiply the perpendicular component of the radius times the force. Or how else could you do it?
You could do the perpendicular force times the momentum arm or the moment arm.
Yeah, you could take the entire moment arm, the entire radius, times just the perpendicular component of the force. But these are really just different ways of writing a more general formula. In general, I would say torque is the entire radius times the entire force times the sine of the angle between them. The reason this works ultimately is that if you want to apply a torque, if you want to make something change how it's rotating, let's say you have this object, you're applying a force to it to make it spin faster or spin slower, maybe even start spinning if it's not already spinning. You can apply a force to it. The more force you apply, the more rotational force, more rotational effect you get. But so the more force means more torque. But if you could apply that force anywhere on the object, where should you apply the force to get the most result?
Farthest away.
Yeah, the further you apply it from the pivot point, the more result you get. If you apply a force very close to the pivot point, it's much more difficult to get it to change its rotation. A force further from the pivot point, it's much easier to change the rotation. So a force applied at a larger radius further from the pivot point produces more torque. And how does angle play into it? Like if I'm allowed to apply a force to this, but I can choose any angle to apply the force, what angle of force would make it easiest to make this thing rotate?
Perpendicular.
Yeah, if I apply a force perpendicular to, specifically perpendicular to the moment arm being the r vector, the radius vector from the pivot point to the location where the force is applied. That has a directionality associated with it. If I apply a force perpendicular to that, I get the most result. So you get the largest result in terms of torque when theta is 90 degrees. That's why we use the sine function here. Sine of 90 degrees is 1. That's the largest it can get. On the other hand, what angle would lead to sine being 0?
180, I'm guessing. I don't know.
Yeah, if you have theta is 180 degrees, then sine is 0, or also what else?
0 degrees, like if it's on the same.
Right. Sine of 0 degrees would be 0, and sine of 180 degrees would be 0. That means if you take your radius vector and apply a force in the same direction, like let's say just grab this and pull, I'm not causing any rotation. Or if we've got a radius vector and I'm applying a force in the opposite direction, if I push this way, that's not causing any rotational change at all. It doesn't cause any torque. So in order to cause any torque at all, you need all three of these to be non-zero. To create torque, to apply torque, you need to apply a force. That force needs to be some non-zero distance away from the pivot point. Like if you just push on the pivot point, you're not causing any torque. So the force needs to exist. It needs to be some non-zero distance away from the pivot point. And it also has to have a non-parallel direction. You can't be pushing straight towards the pivot point or pulling straight away from the pivot point. It's got to be at least somewhat offset from the radius vector. It doesn't have to be perfectly perpendicular, but it can't be parallel. In other words, a push straight towards the pivot point or straight away from the pivot point doesn't create any torque. Any questions on that so far?
Where's the angle measured from?
The angle is measured between the radius vector and the force vector. For example, if we have, let's say you've got some object that's got its pivot points, let's say on this corner here. And let's say the force we're talking about is the weight of the object. The weight of the object, the force of gravity, would presumably be located where on the object?
The center.
Yeah. And that'll be straight down. So let's say this is the force of gravity, but the object is attached in place here. It's attached to a hinge, let's say. The radius vector would be the displacement vector, the distance vector from the pivot point to the location where the force is applied. So if you've got a pivot point and a location where a force is applied, the radius vector is the displacement vector from the pivot point to the location where the force is applied. And then the angle we're talking about in this formula is this angle here.
Okay.
Or alternatively, you could imagine extending the radius vector further in a straight line. And you could be talking about this angle. Those are different angles, but since they are supplementary, they add up to 180 degrees, they will have the same sine function. That is, sine of this angle and sine of this angle will be the same. The radius vector, yeah, the radius vector is the displacement vector from the pivot point where everything's attached to a hinge or something to the location where the force is being applied. And then the theta, the angle, is the angular difference between those directions. Like the radius vector is pointing this way, the force is pointing this way. So one way to interpret theta is if you point in the direction of the radius and then rotate to point in the direction of the force instead, theta is how much you have rotated to change the direction of pointing. So formally, I think I would say theta is this large angle. But if you have two angles that add up to 180 degrees, their sine will be the same. So you may as well just use the smaller angle instead. That's usually going to be easier to work with. But that's what theta means. It's how offset the radius direction and the force direction are in terms of angle. Which means if they're exactly the same direction, like let's say we instead have a force that's pointing, let's say you just grab this square by the center and pull this way. In that case, what's the angle between radius and force?
0.
Yeah, if they're pointing in exactly the same direction, I would say there's a 0 degree difference between them. So you'd have sine of 0, which is 0, meaning that this force produces no torque at all. Likewise, if you have a force pointing exactly in the opposite direction, from here straight towards the pivot point. In that case, if the radius is pointing one direction and the force is pointing the exact opposite direction, what's the angle between them?
180.
Right. And sine of 180 degrees is also 0. So this force pointing straight towards the pivot point also produces no torque at all. In order to produce a torque, you'd have to have some non-zero, non-180 degree angle. And you get the most torque if the force is perpendicular to the radius. So if you apply a force on this diagonal, forming a right angle with the radius vector, that force is going to produce torque most efficiently in the sense of getting the most torque per Newton of force you apply. But you can get torque by applying the force in any direction as long as it's not parallel to the radius vector. Any other questions on that so far?
Sorry, I was trying to compare what you just said to like our DL manual. And so there's like the pivot point at the bottom of the circle, and then the force of 1 is like kind of at the angle, but when you draw the radius to the force vector, it is parallel with it. So does that mean there's no force on it?
No torque.
Or sorry,
Yeah,
no torque.
Yeah, it would definitely still count as a force because it is a push or a pull on the object. But if I understand correctly, you're saying there's a pivot here and you're applying a force somewhere out here, I think.
Yeah, right there, and then it's going like toward the sine theta that you just wrote.
Okay, so like this force here.
Yeah.
In that case, if we draw out the radius vector would be the displacement vector from the pivot to the location where the force is being applied.
Yeah.
And what do you notice about those two directions?
They're in the same, they're parallel.
Right,
like
which means the angle between them is 0 degrees and sine of 0 is 0.
Oh, so so when we're like choosing the angle, it's from the original force vector to the radius?
It's the angle of difference between the radius vector and the force vector.
So then when drawing the perpendicular force, because I thought there was something in the Discord that showed the angle being drawn from like the force to the perpendicular force, and then they called that theta. Is that not correct?
No, the angle should be the angle between the radius vector and the force vector.
The original force vector?
Yeah.
Oh.
In the sense that if you, I think it might be useful to think of theta as how far you'd have to rotate the force to make it line up with the radius vector. In this case, the force is already aligned with the radius vector, so no rotation would be needed at all. And that means theta would be 0, but sine of 0 is 0, so you get no torque.
Okay, so then for most of the problems, is the theta greater than 90 degrees? Because for force 3, it's right across from the pivot point, on the other side of the circle, but it's still at that same direction as force 1.
So we'd have something like this.
Yeah, and then towards the, yeah, exactly. And so for the perpendicular one, I got it just like drawn the radius and then just a straight line across to the left.
Yeah, and
So I
the,
thought that
in
was
terms
like-
of the angle, you could actually interpret the angle two different ways here. You could say the angle theta is the angle between the radius vector and the force vector like this, or you could imagine extending the radius vector and drawing in this angle instead. These are not the same angle. They're two different angles, but the sine of this angle and the sine of this angle will be the same value because of the way we calculate sine of angles on the unit circle. In general, any two angles that add up to 180 degrees, their sines will be the same, but their cosines will be opposites.
Okay, that makes a lot of sense. And so then, sorry, for the radius vector, we could extend the force one, and then our radius would be pointing like to the right.
Well, in the sense that if you extend the force vector in the opposite direction, we'd be talking about this angle, which is the same as this angle, because these are just two lines that cross each other. So these would be, geometrically, we call these vertical angles from each other, and they'd be the same angle. In the same sense that these two angles will also be the same.
I thought for the perpendicular radius vector, we were trying to make it a right angle with the force.
Oh, if you want to draw the perpendicular components, yeah. I was just saying, if you extend the force in the opposite direction or extend the radius further, because you could think of the radius direction as just being an infinite line, and the force direction as being an infinite line. We're looking for the angle between those two lines where they intersect. But if you want to split up the vector in terms of its components, the idea is that instead of using traditional x and y components, we're using a possibly tilted coordinate system based on the vector we already have. So for instance, if we want to split up the force into components, not necessarily the usual xy components, but specifically components based on the radius. If you think of the radius as the foundation of a new coordinate system, if we have one axis that's parallel to the radius and one axis that's perpendicular to the radius. So instead of calling these the x-axis and the y-axis, we're going to call these the parallel axis and the perpendicular axis, in the sense of an axis parallel to the radius vector and an axis perpendicular to the radius vector. Then we can split up the force vector into components based on that new coordinate system. We have a parallel component, sorry, a perpendicular component and a parallel component. So this component is a component of the force perpendicular to the radius, and this component would be a component of the force parallel to the radius. So we might call these F parallel and F perpendicular. And of those components, which one actually influences torque?
The perpendicular component?
Right, that perpendicular component is the component we care about. And mathematically, the reason for that, if we go back to this angle theta, in this case, the angle between the extended radius vector and the force vector, how would you calculate F perpendicular based on this theta here?
Sine.
Right. This horizontal side, the perpendicular side, is going to be sine of theta times the hypotenuse, that is F sine theta. F sine theta is the perpendicular component of the force. So I usually think of RF sine theta as the definition of torque, but you can replace F sine theta with F perpendicular, just the perpendicular component of the force, and ignore the parallel component. So you could write this as R, like the entire radius vector, the actual distance, times just the perpendicular component of the force.
That makes sense. So if we were to do R perpendicular instead of F perpendicular, would we extend the force and then make R more at an angle? Like,
Sure. I think it's probably better to think of it not as extending the force, but as creating a new coordinate system based on the force. So keep the force vector as it is, but use the force, the direction of the force, to create a new coordinate system. We, instead of the usual XY axis, we're going to tilt the axes to have an axis that's parallel to the force. So this is the parallel axis, and another axis that's perpendicular to the force. So this is the perpendicular axis. And then we're going to split up the radius vector into components based on these new axes. So we will have a perpendicular component. And let me erase the circle here to get some more detail on this. We'll have a perpendicular component and a parallel component. So we're splitting up the radius not into X and Y components, but into a component parallel to the force, R parallel, and a component perpendicular to the force, R perpendicular. And again, the angle could be thought of as, which angle would this be? Actually, it might be easier to see this if I draw this on the other side, if we flip the triangle over, because it doesn't really matter which side you draw the triangle on, but sometimes one side or the other is easier to see what's going on. So if we split this up into a parallel component in the same direction as the force, and a perpendicular component, R parallel, which we can ignore, and R perpendicular, which we care about. Putting that angle back in, theta is the angle made between the radius and the, in this case, the extended force. What would sine of theta tell you about this angle or about the sides?
Sine would tell us R perpendicular
Right,
and the radius.
exactly. Sine theta would be R perpendicular over R, which means R sine theta is R perpendicular. So again, although I think of torque as defined as R F sine theta, if you combine F sine theta, you get F perpendicular times the entire radius. Or you could combine R sine theta to get R perpendicular, just the perpendicular component of the radius, times the entire force. So these both work as alternative formulas for torque. You could write it as the entire radius times just the perpendicular component of force, or the entire force times just the perpendicular component of radius. These will all give you the same result because F perpendicular is F sine theta and R perpendicular is R sine theta. So either one of the vectors' entire magnitude times just the perpendicular component of the other vector. Those should all get you the same result because they all just end up being a hidden sine theta anyway. Any other questions on that so far? Then let's get back to the bicep problem as well. If we're dealing with torque, we actually care about where the forces are located, since the torque is all about not only how much force, but also where it is compared to the pivot point and in which direction. So typically for that, instead of just drawing a free body diagram where we treat the whole object as a single point, we want to care about the shape of the object and where the forces are. So we're going to draw these same forces, but in an extended free body diagram. Extended free body diagram or extended force diagram means we're actually going to draw it as, in this case, as a rectangle. In fact, usually a rectangle is enough, no matter what the actual shape is. Like, we don't have to care about the actual shape of the forearm. We can essentially just draw it as a bar. Even just a single line will work. The thickness doesn't really matter here. But the important things we want to keep track of are we've got a pivot point. And now we're going to draw in the forces in terms of where they're located. By keeping track of the same four forces, we've got the muscle force, which is located where?
5 centimeters away from the pivot.
Yeah. The muscle force of unknown strength is 5 centimeters away from the pivot. And then the spring force is how far from the pivot?
30.
Yeah, 5 plus 25 is 30 centimeters away. So the spring force we know is 180 newtons and is from the pivot point is 30 centimeters away. So we can use these as the R values. And there's also force of gravity, which we know is 30 newtons. But how much torque is the force of gravity producing? What would be the angle between the radius vector and the gravity force vector?
180, so 0.
Right, that produces no torque at all because the force of gravity is pulling straight towards the pivot point. the angle would be 180 degrees, sine of 180 is 0, so we get no torque from gravity. If the arm were held at an angle, then gravity would be providing a torque. But if the arm is entirely vertical, then gravity provides no torque at all. So we can ignore that for purposes of torque. And what's the one other force we have here that I haven't drawn in yet?
The pivot point or the joint?
The force of the joint, we don't even know which direction that is, so I'm not even going to draw that. But we at least know that it's at the pivot point. So how much torque does the joint force provide?
The opposite of the combination of the others?
If it's at the pivot point, what's the radius distance?
Oh, 0.
Yeah, any force at the pivot point is 0 centimeters away from the pivot point. So R would be 0 and therefore no torque at all. In general, any force that's at the pivot point or pointing straight towards the pivot point or straight away from the pivot point produces no torque at all. Torque requires a force that's offset from the pivot point and is pointing in some direction that's off center, pointing not directly towards or away from the pivot point. So it looks like the only forces here that provide torques we need to consider are the torque from the muscle and the torque from the spring. And as I said before, those have to add up to 0 because this object is not rotationally accelerating. So we can say torque from the spring plus torque from muscle have to add up to 0. And we can calculate those magnitudes pretty quickly, because what's the angle between each of these radius vectors and the corresponding force vector?
90, so it is the perpendicular point.
Right. Yeah, we don't even need to worry about splitting it up into components. We can just use RF sine 90, and sine 90 is 1, so we just get R times F. So for each of these torques, we can just multiply radius times force. For the spring, that's 30 centimeters times 180 newtons. And since everything here is in centimeters, we don't really even need to do any conversions. We can just leave it in centimeters. And then the muscle torque is only 5 centimeters times an unknown muscle force. And since these are vectors, we also need to take direction into account. Have you seen yet how to determine the direction of a vector? Or direction of a torque vector specifically?
Yeah, the right-hand rule.
Yeah, we can use the right-hand rule. There's several variations on it. The one I usually use is put your hand at, like, let's say we're trying to find the muscle torque. If you put your hand at the pivot point and stretch your fingers straight towards the location of the force, and note that I can still swivel my hand around, but I also want to be able to curl my fingers in the direction of the muscle force. So again, put your hand at the pivot point, stretch your fingers straight towards the location where the force is applied, and swivel your hand until you can curl your fingers in the direction of the force. And then your thumb pointing perpendicular to that will be the direction of the torque. So we say the muscle torque is pointing outwards. That doesn't mean anything's moving outwards. It just means the muscle is trying to create rotation around this axis. The direction of torque is really the direction of an axis of rotation, or an attempted axis of rotation. When we say the muscle torque is pointing outwards, we just mean the muscle torque is trying to make the forearm rotate around that axis, and specifically rotate this way. So torque in the outwards direction means attempting to make the object rotate counterclockwise around that axis. And typically the way we draw an outwards vector is a circle with a dot in it. This is supposed to represent like an arrowhead pointing straight towards you. You see the arrowhead and the tip of it, the point. So a circle with a dot in it is supposed to represent an arrow pointing straight towards the viewer. And if you apply the same right-hand rule to the force of the spring, what do you get for the torque direction?
In.
Yeah. Again, put your hand at the pivot point, stretch out straight towards the location of the force. And now we want to swivel the curl to the right, because that's the direction of the force of the spring. And now my thumb is pointing into the board. So we'd say the torque of the muscle is an inwards torque. Again, not meaning anything's moving in, just means it's rotating around an inwards axis, or trying to make it rotate that way. And we typically draw that as a circle with an X in it, which is supposed to represent an arrow, like with fletching, the feathers at the end going away from the viewer. So a circle with a dot is an arrow pointing towards the viewer. A circle with an X is an arrow pointing away from the viewer. The important thing, though, is these are opposites. So we can treat one of them as the positive direction and the other as the negative direction. Doesn't really matter which is which because they add up to 0, which means their magnitudes have to be equal. We can add this term to both sides. You get 30 centimeters times 180 newtons equals 5 centimeters times force of the muscle. That is our missing third equation. We now have 3 equations with 3 unknowns. And since the torque equation has only one of those unknowns, we can solve for that directly. How would you isolate force of the muscle here? How could you solve for F muscle in this equation?
Oh, just divide by 5 on each
Yeah.
side.
Divide by 5 centimeters. And when you divide by 5 centimeters, centimeters and centimeters cancel out. And we could reduce 30 over 5 to 6 over 1, or just 6. In other words, before we multiply it all out, the force of the muscle has to be 6 times as strong as the force of the spring, which works out to, I think, 1080 newtons. So the muscle has to be providing a tremendous amount of force here. And why is that? Why does the muscle have to be 6 times stronger than the spring? Why is 6 times as much specifically?
Because it's 6 times closer to the pivot point.
Yeah, the spring is 6 times as far away, so the muscle has to be 6 times as strong. This goes back to the idea that torque is radius times force, ignoring the angle for the moment. So if you have one force that's 6 times as far away, the other force needs to be 6 times as strong. Those multipliers have to balance out. So there's always a trade-off when you're dealing with leverage like this. If you are a certain number of times further away, you can afford to be a certain number of times or a certain factor weaker than the other force, and vice versa. The muscle has to be extremely strong, but the trade-off is that it gets the advantage of being very compact. This all fits in a very small space. So if you had the muscle attached further away, the muscle wouldn't have to apply as much force, but it would take up a lot more space and it would have to pull a lot further. The way it's set up here, the muscle has to be very strong, but only has to pull a little tiny bit of distance in order to get the end of the arm to move a much larger distance. So as always with levers, there's going to be trade-offs. It's really just a matter of what are you trying to accomplish and what can you afford to invest a lot of effort in. And once we have that muscle force, we can now substitute that into the other equation and find the X component of the joint force. And then with the X and Y components of the joint force, you can use the usual trigonometry to find the magnitude and direction of the force from the elbow. And I think that should be everything we need. We know the muscle force, we know now, or we can find the X and Y components of the joint force, convert to magnitude and direction. So that solves the whole system. Any other questions on that? All right, try similar approaches on other examples to get some more practice. I think you should be able to find some practice quizzes with similar situations. In general, whatever situation you're dealing with, try to choose one object that has lots of forces acting on it that you care about. Draw out an extended free body diagram for that object. Label all the forces that are acting on it or even could be acting on it, including direction and location, and try writing out this system of equations. The forces add up to 0, and that can be split into X and Y components in a two-dimensional problem, and the torques add up to 0. As long as you can get a system of as many equations as you have unknowns, then that's a system that can be solved. So try out some examples with that, and I will see you next time.
Thank you.
You're welcome.